When we are investigating differentiability, we have a couple of different components that need to be in place. If a function is going to be differentiable, meaning we can draw in a tangent line and we can find the slope of that tangent line, then we need to make sure that the function itself is actually continuous. So here at both point A and point B, we do have a function that is continuous, meaning from the left side and from the right side, we do have a limit. There is a point at each one of those x values, and the limit and the point all match up together. But not only do we need to be continuous, we need to make sure that we can actually draw in one tangent line. So for point A, this is what's the case going to be, because at point A, we're going to have that single point, and we're going to have a tangent line that can be drawn in here. One of the things that we want to be looking at would be what is the slope of each tangent line as we're approaching from the left and approaching from the right. So in other words, we're almost looking at the limit of what the derivative is doing. So one thing that we would be looking at is the limit as x approaches a from the left of our derivative of the function, and making sure that that matches up with what happens as x approaches a from the right of the derivative. In other words, if we try to take a look at what's going on with the slope on the left-hand side, so what's going on with the slopes of this part, and what's going on with the slopes of that part, and making sure that they are actually equal to each other when we hit x equals a. If you look at x equals b, we're going to notice that that's not really the case. All of the slopes on this side are negative. All of the slope on the right side of b are positive. So we actually don't have a match for what happens at b. They don't round out. They don't try to even themselves out or approach zero. This one is approaching a negative value. The one on the right is approaching a positive value. So therefore, the limits of your slopes are not really going to approach each other. Even though b is continuous, we have kind of this corner that's sitting there. So when we're tackling a piecewise function and trying to figure out if we're differentiable, we are, number one, ensuring that we are in fact continuous between x equals 2 on the left and x equals 2 on the right. We're going to make sure that both pieces come together. But we also want to make sure that our derivatives match on the same side. So we're going to take a look at two different sets of limits, one to prove the continuity and one to prove that the derivatives would match. If that's the case, then we would be differentiable at x equals 2. So I'm going to start first and foremost with the continuous piece. Step number one, we're going to prove the continuity. So for that, I'm going to examine the limit as x approaches 2 from the left of our function and make sure that that's equal to the limit as x approaches 2 from the right of our function. So why don't you pause for a second and try to figure out what that might look like. So on the left, we're using x squared plus 1. On the right, we're using 4x minus 3. When we plug in x equals 2 into each one of those pieces, both sides are heading towards a value of 5. And since we do have that equal to sign under one of the inequalities, it means that the x squared plus 1 also has a point value, or in other words, f of 2 is also equal to 5. So we have a point that exists, we have a limit that exists, and the point and the limit share the same value. So we know that f of x is in fact continuous at x equals 2. So the next part is to take a look at what happens with the derivatives. Do your derivatives match up? So we're basically going to do the exact same thing right here, but we're going to be using f primes. So we're going to take a look at the limit as x approaches 2 from the left of f prime of x, and make sure that that's the same as the limit as x approaches 2 from the right, again, of f prime. We're going to make sure that the slopes are going to match as we approach x equals 2. So right here, we're given f of x. When we want to find f prime of a piecewise, we are literally going to take just the derivative of each individual piece and keep the same domain restrictions. Here's what I mean by that. We have a top piece that is x squared plus 1. Its derivative would be 2x plus 0. And we're going to keep this domain piece. I'm just going to make it x is going to be less than 2 because we're not really sure what's happening exactly at x equals 2 yet. That's what we're trying to investigate. The bottom piece is 4x minus 3. Its derivative would just be a 4 plus a 0. And again, it's for x is greater than 2. So now we're going to use these to do our limits. The limit as x approaches negative 2 from the, or x approaches 2 from the left is going to be of the piece 2x. And in this case, we're plugging in x equals 2. The limit as we approach 2 from the right of f prime is a 4. And so we're looking at 4 is equal to 4. And so our derivatives do match as a limit approaching from both sides. So because we are continuous and because our derivatives are going to match from both sides, we can say that f of x is differentiable at x equals 2.